All right, so our next video will be on the subject of molecules and molecular orbital theory. And but before we get into that, let me first briefly discuss a couple of topics that we're not covering in these lectures that are primarily from Chapter 8 on the quantum mechanics of multi-electron atoms. And one of the topics that we'll be skipping is, again, skipping in these lectures, is Hartree-Fock self-consistent field method. I have some written written section on this in the PDF lecture notes, and that will go into that in enough detail, I think, to give you some notion of what's happening in Hartree-Fock self-consistent field. Very important method. It's not just for electrons, or sorry, in electrons in it's not just for multi-electron atoms. It's also for molecules, as it turns out. And that said, it's really a big subject that would require multiple lectures, maybe a couple hours of lectures. And we want to move on to talking about molecules, and so we're skipping that for the moment. But it has a few interesting ideas that are discussed in the other lecture notes. The other thing that another thing that we're going to be dropping from these lectures that I typically don't cover is term symbols, which is a way of representing complicated electronic configurations in a nice compact form, and this is very useful for making tables of the relative energy levels of different excited electronic configurations. And this is important. Of course, it shows up in things like atomic absorption or atomic emission spectroscopy. There are all these different term symbols that correspond to the various atoms' electronic states. However, I find that it's not, from my perspective, not terribly interesting per se in itself, and it's more of an accounting issue, at least again from my perspective, based on the things that I like to study. Other people, I'm sure, have a different opinion of term symbols. And another thing that we're going to be skipping is ionization energies of atoms. And this is something that perhaps gets covered in some of your prior chemistry courses on some level. It's hard for us to go do a real deep dive. Of course, these ionization energies are well predicted by Hartree-Fock theory, and they're of historic importance. And they show important periodic trends that say ionization energies of things like, you know, the first column, of sodium and lithium and so on has very low ionization energies, and there's a periodic trend as you move across the periodic chart from column to column. And of course, ionization energies of atoms are important for a variety of methods that involve ions, particularly ions in vacuum, and those would be things like mass spec, atomic absorption and emission spectroscopy, and so on. That said, I don't have a lot to really say about ionization energies, and so we're going to leave that to perhaps other courses where these concepts are more front and center. Now let's move on to the subject of this lecture, which is molecules and molecular orbital theory. And in particular, we're going to be looking at H2 plus molecule ion, and we'll also be looking into the Born-Oppenheimer approximation. And we're going to be developing this concept of molecular orbitals, MO, as a linear combination of atomic orbitals, MOLCAO theory. It's a way to construct molecular orbitals starting from the atomic orbitals of the various atoms that make up the molecule. Okay, without further ado, let's move on to H2 plus. H2 plus molecule ion, right? So this would be two nuclei or two protons, two hydrogen nuclei, and one electron. It is arguably the simplest molecule. And so that seems like a good place to start. And of course, after developing a theory for H2 plus, we will see what we can do to expand it to look at or to describe more complicated molecules, ones with two or more electrons, and eventually we will talk about the next simpler molecules, things like the homonuclear diatomic molecules, things like, in addition to H2, looking at things like C2 or N2 or O2, and having a theory and a description and being able to make some predictions about these molecules. So as we often do, I like to start with a diagram of the various particles and forces and setting up our coordinate system. And so let's go ahead and do that. First of all, we're going to have some nucleus A, and it's going to have a positive charge. And then there's going to be some nucleus B that also has a positive charge, right? So we have our two protons. There's a distance between the two protons, right? This is a molecule, so there's some bond length, and we'll call that capital R. And then we have an electron, and we're going to draw our electron as being sort of somewhere in between those two nuclei, maybe temporarily off to one side. Of course, it's going to be moving around, and there's going to be a distance between that electron and nucleus B, so we'll call that R1b. And there's also going to be a distance between the electron and nucleus A, we'll call that R1a. And that sets up our coordinate system. We've identified our particles, we've placed them somewhere in our coordinate system, and we've specified the coordinates of all three particles relative to one another. The next thing we want to do is look at the forces or the interaction potentials between these various particles. Related to this R1b, we're going to have a Coulomb attraction between the nucleus B and the electron, and that Coulomb attraction is going to be minus e squared over 4 pi epsilon naught R1a, R1b, sorry. And of course, there's going to be a similar term for R1a. and that would be, again, another Coulomb potential. In addition, there's going to be this electrostatic repulsion between the two nuclei. We can't ignore that, right? We have to count all of the forces in our system. And so there's going to be an internuclear repulsion, um, and it's going to have a form e squared over 4 pi epsilon naught big R, right, where big R is the distance between those two nuclei. So we have an attractive interaction between the electron and nucleus A. We have an attractive interaction between the electron and nucleus B, and we have a repulsive interaction between nucleus A and nucleus B. Okay, the next step is, of course, to develop a Hamiltonian. All three of these particles can move, and of course, we're not so interested in, say, the molecule moving as a unit through space. That's, translation of overall net translation of the molecule. That's something that we've dealt with already in the sort of particle in a box. So this would be a molecule in a box for that kind of motion. There's also going to be a vibrational interaction, which we're going to ignore. And so we're going to ignore translation of the molecule as a whole. Or as a unit. And we're going to temporarily ignore vibration. And it turns out that there's a framework within which we can ignore these things, and that's called the Born-Oppenheimer approximation. And Oppenheimer, in addition to being the father of the atomic bomb, was, of course, also involved in some fairly early quantum mechanics. And the basic idea behind the Born-Oppenheimer approximation is that, first of all, we're not that interested in translation of the molecule as a whole. That's not really part of the Born-Oppenheimer approximation. However, there is this issue that electrons are small and light. They have a small mass. And so they move relatively quickly relative to these big, heavy nuclei. And so there's a separation of timescales. Between nuclear motion and electronic motion. So when the electrons are moving around, what they see are that the nuclei are essentially stationary at some fixed distance r. And so you can imagine that the nuclei can move, but there isn't going to be necessarily a straightforward connection between electron motion and nuclear motion. They're going to be sort of decoupled. They're going to occur on different time scales. In other words, the nuclei will move on their own time scale, and the electrons will just sort of react to that motion to try to minimize their energy. And similarly, the nuclei are going to be moving in a more or less a potential energy surface or a force, a net force, that is given by the sort of averaged, smeared out electron density of the electrons. And so this allows us to have a relatively simple Hamiltonian. We can ignore vibrational energy and develop a Hamiltonian that looks as follows, that our electronic Hamiltonian, right? We'll just sort of ignore the nucleus for the time being, and we have a Hamiltonian for the electron, and this is for H2 plus, is going to be equal to minus h bar squared over 2 me del squared for the electron. And there's just one electron, so there's not going to be two del squared terms, one for each electron. There's only one electron in this molecule ion. We can try adding another electron later, but that's a different model, different Hamiltonian. And then we're going to have this Coulomb terms, this set of 3 Coulomb terms. We're going to have minus e squared over 4 pi epsilon naught, and 1 over R1a plus 1 over R1b minus 1 over R. And we notice that we've got this sign out in front of all of these Coulomb terms, this minus sign, minus e squared over 4 pi epsilon naught. And so when we multiply that by the minus 1 over R, that's going to give us a positive or repulsive internuclear potential. So this is a somewhat complicated looking Hamiltonian, but not really more complicated than the helium Hamiltonian, and of course it has the same number of particles as the helium Hamiltonian. One of the nice things is we can actually end up, and one of the features of the Born-Oppenheimer approximation is, since the nuclei are held as fixed within this electronic Hamiltonian, then we're going to treat R as a variational parameter. And that brings me to the end of part 1 of this lecture on the H2 plus molecule ion.